Hey guys, welcome back. Now let's get started with our day 14 walkthrough. Here the learning objectives are: what is machine learning, basic machine learning structures and algorithms, using neural network to predict defective toys. Introduction. Over the last decade, there has been a massive boom in artificial intelligence and machine learning systems. Just in the last couple of years, the release of ChatGPT has taken the world by storm. However, how these systems actually work is often shrouded in mystery, leading a lot of snake oil sales tactics. In this task, we will provide you with a glimpse into the world of ML to help demystify this incredibly interesting topic. We will create our very own neural network that can be used to detect defective toys. Zero to hero on artificial intelligence. Before we can create our own AI, we need to learn some of the basics. First of all, let's discuss the two terms. The term AI is used in broad strokes out there in the world, often incorrectly. We have to be honest with ourselves. AI can't just be a bunch of if statements. A better term to use is machine learning. Machine learning refers to the process used to create a system that can mimic the behavior we see in real life. This is because there is intelligence in real life and its structures. The field is incredibly broad, but there are a couple of popular examples: genetic algorithm, particle swarm, neural networks. There are many more machine learning structures, but we'll stick to the neural networks for this task as they are the most popular, and while there is a significant amount of maths involved in implementing an ML structure, we'll be abstracting this information. If you want to learn more, you can start here and then work your way up. So, learning styles. First on our list of machine learning basics to cover is neural networks learning style. In order to train our neural network, we need to decide how we'll teach it. While there are many different styles and subsets of style, we will only focus on the two main styles for now. Supervised learning. In this learning style, we guide the neural network to the answers we want it to provide. We ask the neural network to give us an answer and then provide it with a feedback on how close it was to the correct answer. In this way, we are supervising the neural network as it learns. However, to use this learning style, we need a dataset where we know the correct answers. This is called label dataset, as we have a label for what the correct answer should be given the input. Unsupervised learning. In this learning style, we take a bit more of a hands-off approach and let the neural network do its own thing. While this sounds very strange, the main goal is to have the neural network identify interesting things. Humans are quite good at most classification tasks. For example, simply looking at an image and being able to tell what color it is. But if someone were to ask you why is it that color, you would have a hard time explaining the reason. Humans can see up to 3 dimensions, whereas neural networks have the ability to work in a far greater dimensions to see patterns. Unsupervised learning is often used to allow neural networks to learn interesting features that humans can't comprehend that can be used for classification. A very popular example of this is restricted Boltzmann machine. For this task, we will focus on supervised learning. It's an easier learning style for learning the basics, including basic network structure. Basic structure. Next on our list of machine learning basics to learn is the basic structure of a neural network. Sticking to the very basics of ML, a neural network consists of various different nodes that are connected as shown in the animation below. As shown in the animation, the neural network has 3 main layers. Input layer. This is the first layer of nodes of the neural network. These nodes each receive a single data input that is then passed to a hidden layer. This means that the number of nodes in the layer always matches the neural network's number of inputs. If our network takes the toy's length, width, and height, there will be 3 nodes in the output layer. This is the last layer of nodes in the neural network. These nodes send the output from the network once it has been received from the hidden layer. Therefore, the number of nodes in this layer will always be the same as the number of outputs. For example, if our network outputs whether or not the toy is defective, we will have one node in the output layer for either defective or not defective. Hidden layer. This is the layer of nodes between the neural network's input and output layers. With a simple neural network, this will only be one layer of nodes. However, for additional learning opportunities, we could add more layers to create a deep neural network. This layer is where the neural network's main action takes place. Each node within the neural network's hidden layer receives multiple inputs from the node in the previous layer and will then transmit their answers to multiple nodes in the next layer. Now that we understand the basic layout of neural networks, let's zoom in on one of the nodes of the hidden layer to see what's actually going on. As mentioned before, we will simplify the maths quite a bit here. In essence, the node is receiving inputs from the nodes in the previous layer and adding them together. and then sending the output to the next layer of nodes. There is, however, a little bit more detail in this step that's important to note. Inputs are not directly added. Instead, they are multiplied by a weight value first. This helps the neural network to decide which input should contribute more to the output than others. The addition's output is not directly transmitted out. Instead, the output is first entered to what is called the activation function. In essence, this decides if the neuron or node will be active or not. It does this by ensuring that the output, no matter the input, will always be a decimal between 0 and 1. Now that we understand the neural network structure and how the layers and nodes within it work, let's dive into how the network is trained. There are two steps to training the network: the feed forward step and back propagation step. Feed forward loop. The feed forward loop is how we send the data through the network and get an answer on the other side. Once our network has been trained, this is the only step we perform. At this point, we stop training and simply want an answer from the network. To complete one round of the feed forward step, we have to perform the following. Normalize all of the inputs. To allow a neural network to decide which inputs are most important in helping to decide the answer, we need to normalize them. As mentioned before, each node in the network tries to keep its answer between 0 and 1. If we have one input with the range of 0 to 50 and other with a range of 0 to 2, our network won't be able to properly consume the input. Therefore, we normalize the inputs first by adjusting them so that their ranges are all the same. In our example here, we would take the inputs with a 0 to 50 range and divide them all by 25 and change their ranges to 0 to 2. Feed the inputs to our nodes in the input layer. Once normalized, we can provide one data entry for each input node in our network. Propagate the data through the network. At each node, we add all the inputs and run them through the activation function to get the node's output. This output then becomes the input for the next layer of nodes. We repeat this process until we get a network's output layer. Read the output from the network. At the output layer of the network, we receive the output from our nodes. The answer will be a decimal between 0 and 1, but for decision making, we'll round it to get a binary answer from each output node. Back propagation. When we are training our network, the feed forward loop is only half of the process. Once we receive the answers from our network, we needed to tell how close it was to the correct answer. This is back propagation step. Here we perform the following steps. Calculate the difference in received outputs versus expected outputs. As mentioned before, the activation function will provide a decimal answer between 0 and 1. Since we know that the answer has to be either 0 or 1, we can calculate the difference in the answer. The difference tells us how close the neural network was to the correct answer. Update the weight of the nodes. Using the difference calculated in the previous step, we can start to update the weights of each input to the nodes in the output layer. We won't be diving deep into this update process, as it involves a bit of complex maths to decide what update should be made. Propagate the difference back to the output layers. This is where the term back propagation comes from. Once the weights of the nodes in the output layer have been updated, we can calculate what difference would be made for the previous nodes. Once again, this difference is then used to update the weights of the nodes in the layer before being propagated backwards even more. We continue this process of back propagation until the weights for the input layer have been updated. Once all the weights have been updated, we can run another sample of data through our network. We repeat this process with all the samples in order to train our network. Dataset splits. The last topic to cover before we can build a network is the dataset splits. Let's use an analogy to explain this. Let's say your teacher constantly tells you that 1 plus 1 is equal to 2 and 2 plus 2 is equal to 4. But in the exam, your teacher asks you to calculate 3 plus 3. The question here is, have you just learned what the answer is? Or did you learn the fundamental principle required to get the answer? In short, you can overtrain yourself by learning the answers instead of learning the required principle itself. The same thing can happen with neural networks. Overthinking is a big problem with neural networks. Training them with data where we know the answer, so it's possible for the neural network to simply learn the answers, not how to calculate the answer. To combat this, we need to validate a neural network is learning the process and not the answers. This validation also tells us when we need to stop a learning process. To perform this validation, we have to split our dataset into 3 datasets below. Training data. This is our largest dataset. We use it to train the network. Usually, this is about 70 to 80% of the original dataset. Validation data. This dataset is used to validate the network's training. After each training round, we send this data through our network to determine its performance. If the performance starts to decline, we know we are starting to overtrain and should stop the process. Usually, this is about 10 to 15% of the original dataset. Testing data. This dataset is used to calculate the final performance of the network. The network won't see this data at all until we are done with the training process. Once the training is complete, we send through the testing dataset to determine the performance of a network. Usually, this is about 10 to 15% of the original dataset. Now you know how a basic neural network works. So now it's time to build our own. Now let's go ahead and fire up a machine. Now that we have covered the basics, we are ready to build our very own neural network. Start the machine in the top right corner. It'll show you a split screen after 2 minutes. You can find the files you'll be working with on the desktop in the neural networks folder. You are provided with the following files: detector.py. This is the script where we will build our neural network. Some of the selections have already been completed for you. Dataset train.csv. This is your training dataset. In this dataset, the ELs have not only captured the measurement of the toys for you, but also whether the toy was defective or not. We will use this dataset to train, validate, and test our neural network model. Dataset test.csv. This is your testing dataset. In this dataset, the ELs have not only captured the measurements of the toys, due to the sheer volume of the toy pipeline, they were unable to determine if the toy was defective or not. Once we have trained a neural network, we will predict which of the entries in the files are defective toys for MexKD to remove from the pipeline. Our first step is to complete the detector.py script. Let's walk through the initial code. The first few lines are all library imports that we need for our neural network. We will make use of pandas to read our dataset and scikit-learn for building a neural network. Next, we will load the datasets. In our case, there is a training and testing dataset. While we have the labels for the training dataset, we don't have them for the testing dataset. So while we can perform supervised learning, we will only know our neural network's true performance once we have uploaded our predictions for review. Once the dataset is loaded, we need to make sure that the inputs are numeric values. One of our data types is toys color scheme. In order to provide this data to our network, we will encode the colors to numbers. Lastly, we load the data. Variable X is used to store a training dataset together with its label stored in variable Y. Lastly, test X stores the testing dataset that we'll provide to perform the predictions on. We'll now start to add the code required to build and train our neural network. We'll do this in steps to perform the actions mentioned above. Now let's open up the terminal. Okay, so now let's open our script using Vim. So coming back, creating the datasets. First, we need to create the datasets. In our case, we will use a 80-20 split. We will combine our validation and testing datasets, as we will use a completely new data for our testing dataset. To do this, we have to add the following line in our code. Let's copy this line first. So let's paste it here. This will split our training dataset into two. X-train contains the training data and X-validate contains the validation data. Y-train contains the labels for our training data and Y-validate are labels for validation data. Normalizing the data. Next, we need to normalize the data. We can do this by adding the following line in our code after the insert normalization code here. As you can see from the lines of code, we cannot cheat by determining the normalization on either the validation or test dataset. The normalization vector is only created from the trained data, which is then applied to all three datasets. Now let's copy this. Let's paste it here. Training the neural network. Finally, we can train our neural network. First, we will create a classifier with the following code after the insert classifier code here. So let's copy this. Let's paste it here. You can find more information on this specific classifier here. Here's a bit of explanation of what the values are doing. Solver. This is the algorithm used to update the weights. This is a classic backpropagation algorithm, but others can be used as well. The alpha value is used for the regularization of the neural network. We won't dive too deep into the maths here, but we have selected fairly default value. Hidden layer size. This tells us the structure of the hidden layers in our neural network. Based on the provided configuration, we will have 2 hidden layers with 50 nodes in each. Max iter. This sets a cap on the number of iterations we can train our neural network before it is forcibly stopped. Next, we can train a classified with the following code. Insert classified training code here. So let's copy this. Let's paste it. When this step is complete, we have successfully trained a neural network. Validate a neural network. The next step is to validate a neural network. To do this, we can ask the network to predict the values based on the validation dataset with the following code added after the insert classify validation prediction code here. Let's copy this. Let's paste it here. As you'll see, when you execute the script, predictions are significantly faster than training the network. This is why neural networks can actually be used in real-life applications, as the prediction rate is incredibly fast once the network has been trained. We can determine the accuracy of a classifier by comparing the two arrays with the following code. Saving the poison toy pipeline. Finally, as a last step, we can now ask a neural network to make predictions on the testing data that was not labeled by the else with the following commands after the code. Insert classifier testing prediction code here. So let's copy this. Let's paste it here. This is it. We are finally ready to train and run our network. From the terminal, now run the application. These predictions will be saved to a file. Upload your predictions here to see how well your neural network has performed. If your accuracy is above 90%, you will be awarded with the flag. Now let's open up the browser. So here's the file. Let's upload this. Now let's answer the questions below. What is the other term given for artificial intelligence or subset of AI meant to teach computers how humans think or nature works? Okay, so that is machine learning. What machine learning structure aims to mimic the process of natural selection and evolution? That is genetic algorithm. What is the name of the learning style that makes use of labeled data to train a ML structure? Okay, so that is supervised learning. What is the name of the layer between the input and output layers of neural networks? So that is hidden layer. What is the name of the process used to provide feedback to the neural network on how close its prediction was? So if you remember, that was backpropagation. What is the value of the flag you received after achieving more than 90% accuracy on the submitted predictions? So now we have completed our day 14 walkthrough. Thank you for watching my video and stay tuned for more.